So you just saw how that RC circuit worked when we had the voltage going through a resistor and measuring, and then to a capacitor to ground. We measured the voltage across that capacitor. All we've done here is just flip where these two are. We've put a resistor where there was a capacitor and a capacitor where there was a resistor. So the voltage drop across the capacitor is going to be the same. It's the same circuit, right? All we're doing is measuring a different voltage drop. We're measuring the voltage across the resistor. Okay, so the voltage drop across the capacitor is the same. And remember, what we're doing is we're taking our input signal, going from 0 to some voltage at Vs instantaneously. Okay? So we can now think about what is the voltage across this resistor, right? So again, we have our equation from Kirchhoff's equation for our loop voltage, right? Okay, we can now put in our value for Vc here. Okay. Right, and we can just, using the equations here, just simplifying using the algebra, and this is, remember, Vi is going to be equal to Vs, because we're just going, the input is just going from 0 to Vs. We can write our equation for the resistance drop across our, for the voltage drop across our resistance, right? So this is just going to be Vs e to the minus t over Rc. Okay? So let's just rewrite this over here again. Vr is equal to Vs e to the minus t over Rc. And let's do the same thing we did before with our capacitor analysis. Let's say t equals 0. What's going to happen here, right? So we're going to get Vr is equal to Vs e to the 0. So Vr is equal to Vs. Okay, so initially at time 0, the voltage drop across, all of the voltage drop will be across our resistor. Again, when we have this transient, basically all the voltage drop will be here. Again, does this make sense, right? We have a very rapid transient. We have said before that during a transient, our capacitor is going to act as a short. So effectively, we just have a circuit which just has a single resistor with this voltage drop only across this resistor. So that's what we're actually measuring. Okay? If we now think about it in time going to infinity, over a long period of time, when we reach steady state out here, okay, so in that case, we put in Vr is equal to Vs. Time goes to infinity. This is going to go to 0 times 0. So Vr equals 0. Okay? So as we get to steady state voltages, right, the voltage drop across our resistor is going to go to 0. Again, does this make sense? We now have a steady signal that's going, and we've said that our capacitor, there's no current will flow when there's a steady input voltage, right? And in that case, basically, it's acting, our capacitor is acting to open our circuit, right? So in that case, there's no current flowing, and there's no voltage drop across our resistor. So again, now we've just taken our RC circuit, and depending upon what we measure, we can either pass transient signals, as we do in this case by measuring the voltage across the resistor, or we can pass the steady state component by measuring the voltage across the capacitor. Okay? So let's just go now look and see how the voltage across the resistor actually develops in response to the square wave. We expect it to be something like this, where it only passes the transient signal. When it's steady state, it goes back to 0. So this is V out if this is V in. Okay, so let's go take a look.